with what we call logic and reasoning. All right. Chapter 2 starts out with like logic and reasoning, and what that means and what that entails is that we're going to map like you don't normally map. Okay. What we're going to do is we're going to take arguments. We're going to take valid ways of doing things and writing them out in different sense of geometry. Okay. What we're going to talk about are called, more specifically, what are called conditional statements. And that's what we're looking at today, conditional statements. Okay. From past experiences, no, not related. You got notes to keep going, okay? So what happens here with conditional statements is that most of the time you guys have actually seen some of this before. You probably just didn't know what all of it had meant. Okay? Now, what we're looking at is what we call a conditional statement. Conditional statement is just basically an if-then statement. It's an if-then statement. Yeah, right. I can give a counterexample. I'll wear plaid shorts any day. What we're talking about here are things called if-then statements. And just like Ms. Sorge said, if it is second hour, then you were in geometry class. Well, that's a true valid statement for you guys, not a true valid statement for other people because they might not necessarily be in the geometry class. So that's the idea. You've seen hypothesis, you've seen that scenario, that setup, that write-up before, because you've dealt with it in terms of science classes. You've dealt with it in terms of what's that? Let's worry about this now. Worry about that later. Okay? That way you don't fall behind. So what we're looking at today, like I said, is we're going to take it and put it in terms of definitions via geometry. For example, two angles are supplementary if they are a linear pair. That was one of the definitions we talked about last chapter. We dealt with linear pair. We said linear pair angles are two angles that share a common vertex that they add up to equal 180. Therefore, they work supplementary. Well, what we can do with that is we can take just a generic statement and convert it into what we call an if-then statement. Well, it's shaken. So what we do is we take what's called just a plain old boring statement or definition or whatnot, and we convert it into what we call an if-then statement. So if two angles are supplementary, then they are a linear pair. That's one way of writing it. Okay. If-then statements don't necessarily have to always be true. What happens with a lot of these things, we can say that they are true or false, and we can say that they are true or false, or we can say that they are false by saying giving what's called a counter. Now, this example here, where we have if two angles are supplementary, then they are a linear pair. Is that true or false? Actually, it's false. This is technically what we would call a false statement. That's a false statement. The reason being, linear. Well, go ahead. Now, what happens here, remember, what happens here, when you're dealing with a linear pair, that means that they have to be on the same line. Supplementary angles don't necessarily have to be on the same line. So, what I can say is what we call a counterexample. And I'll show you what that means here in a second. Those two angles are supplementary, but they're not a linear pair. Those two angles are supplementary, but they're not a linear pair. So what I'm getting at here is this thing called a counterexample. A counterexample is any statement that can disprove and if then. Let's leave it at that. Make it real generic. Make it real generic. So counterexample is anything that you can come up with to disprove an if-then statement. If it is Tuesday, then I'm going to have corned beef. Well, I didn't have corned beef today. I'm not going to have corned beef. I'll just make something else up. It's anything that can disprove something. Excuse me. Like I said, if it's second hour, then students are in geometry. Well, not all students are in geometry second hour. You can say some students are in English. Some students are in gym, right? A really common example goes along with a statement like this, where we'll say, a really easy one. If you are a teen, teenager, then you are 16. It's false. It's false because what would be your counterexample? I'm 15, not 16. Exactly. You could be 17. You could be 18. All right. That's the idea here. A counterexample is going to be anything that can disprove something else. All right? That's where that comes from. That's where that comes from. So what we do with these conditional statements, this hypothesis conclusion, we write it out in terms of what are called P's and Q's. You guys ever heard the old saying, mind your P's and Q's? That's where this comes from. All right. This is where that comes from. They call it, it's this if-then statement, hypothesis, conclusion. We say, if P, then Q. This is where that idea comes from. And there's a whole drawn out thing of what we call truth tables to this, about how this stuff works itself through. We start with the idea of P's and Q's. P being the hypothesis, Q therefore being the conclusion. If two angles are congruent, then they have same measure. If two angles are congruent, then they have the same measure. Bless you. True or false? It's true. By the definition of congruency, that means that they have to have the same measure. So by saying that if two angles are congruent, then that means they must have the same measure. So what is your hypothesis and what's the conclusion?
They must have the same measure.
What's the hypothesis? What's the conclusion? Well, the hypothesis is the first part, which is? Right. Okay. The hypothesis is quite literally right in here. If two angles are congruent. Okay? If two angles are congruent, that's your hypothesis. Which means it brings conclusion. P implies Q. You'll see you'll hear it said like that. If P then Q, P implies Q. Okay. Now, I'm probably not too far off by assuming that you guys have actually seen hypothesis, if-then statements, probably more often than not, usually in a science class. Now, what we do is we use these a lot in geometry to show how things work, to show that things prove that things are congruent, prove that things work together. It's the idea of understanding hypothesis conclusion. You've all heard this. If this had been an actual emergency, then the signal would have been followed by official information. And then we have a thing on the TV, all those noises and stuff. All right. So again, what would be the hypothesis of this? Yes, sir. Exactly. The hypothesis is, if this was an emergency, so the hypothesis, if an emergency, what would the conclusion be? Yeah, you get other official information. All right. This really isn't a very difficult concept. What's weird about this is that we're mathing with a lot of words today. Over the next few days, we're mathing with a lot of words, and that's what's different about chapter 2. Really, in geometry, it's really not much math, is there? There's a little bit of stuff, because what we start to do in chapter 2 is we build up the background knowledge of how to make these valid arguments using hypothesis conclusions and stuff. And eventually, what we will get to is we will do, I don't know if I showed you guys this yesterday. I think I showed the other class. We're going to get to the idea of what's called a 2-column proof. But in order to do that, what we start with is something fairly simple. We solve a 2 or 3-step algebra problem, and we list all the reasons as to why we are doing this by properties. Well, if you have subtraction, then you have to undo it with addition. It's the idea that we're using this hypothesis conclusion idea to start the argument to a proof. Okay? That's where the stuff comes from. So let's take a statement and turn it into an if-then. And that's one of the very first things that we do here. We take the statement, we turn it into an if-then statement, and then we can do things. So I start with the idea. Thank you, sir. If I start with the idea that perpendicular lines intersect, I want to rewrite that into the idea of an if-then statement. Yes, ma'am. Yeah, and do you even need to put in those extra words, the 2 lines? Yeah, you're not wrong at all. But in the real scope of the most generic sense, if you have perpendicular lines, then they intersect. What you said wasn't wrong. If you have 2 perpendicular lines, then they intersect. If you have perpendicular lines, then they intersect. It's kind of the same thing, isn't it? You're not wrong, but a lot of times what I want you to do is think of it in the most generic, basic senses you can. All right, does that make sense? It takes a little while to get used to the idea that you don't have to come up with extra words. So here's what I would say. If you have perpendicular lines, is it okay to use symbols for these things? You guys remember that symbol for perpendicular, right? You guys remember that? They use that upside down T? Yes, no? Oh, okay. So back in algebra, you guys had parallel and perpendicular lines via slopes and stuff. Okay? You had to have, because you all took algebra, and I know this is an algebra subject, and we again here in the chapters. That symbol, this upside down T, stands for perpendicular. I use that all the time because I don't want to write the word perpendicular. Okay. So if you have perpendicular lines, then they intersect. Hypothesis. Yes, sir. Conclusion then? Perfect. Yeah. Is that true or false? It's true. In order to have perpendicular lines, by definition, they have to intersect because what do they create? Very good. They create 90-degree angles. So by definition, this is a true statement. Okay? This is a true. Okay. Now, let's flip-flop it. So we went with, oops, sorry, this was hypothesis, conclusion. P implies Q. Let's try something different. Write it as Q implies P. Flip-flop the hypothesis and the conclusion. Of that sentence, we're going to take the sentence, the conditional statement, if you have perpendicular lines, then they intersect. And we're going to flip-flop it to say conclusion, then hypothesis. What do you got? Instead of would be, then they are. Yeah, exactly. All right, see how I'm going with that? Because you want to use if then, not would be. If then. Exactly. All right. So if I flip-flop them, it doesn't necessarily always mean it's a true statement. So here's what we have. I can say if you have intersecting lines, then they are perpendicular. Is that true or false? It's false. It's false. This is a false statement because when lines intersect, do they have to be perpendicular? No. So, counterexample. If you have a false statement, that means that you were able to create what's called a counterexample. Now, counterexamples, like I said, can be any statement that disproves something. A lot of times, a statement can be considered a diagram. If lines are perpendicular, what do we put in the corner when we intersect them? A little box, right? So, couldn't I just draw and just say that this is 100 degrees? Isn't that a counterexample? That's all you have to do. What you're doing is that you're coming up with some way of disproving a statement. Just like we did earlier, like you said, Quinn, where we had the, if you were a teenager, then you were 16, you said false. I'm 15, but I'm a teenager. That idea there is by saying the statement was falsified, disproven, I should say, via your counterexample. Same idea here. If you started with if two lines are perpendicular, then they intersect. That's true. Flip-flop it. If two lines intersect, then they are perpendicular. Well, that's false because they don't have to be perpendicular. They could be 100 degrees, 2 degrees. It doesn't matter. Right? It doesn't matter. All right. So what we did here is we did what's called a converse of a statement. What we start right now, oops, I don't have an eraser here. What we have going right now is we have what's called a conditional statement. We have our conditional, which is P implies Q. Then we have what's called a converse. Q implies P. All you do is you flip-flop the conditional. Okay? Your if-then statement, your original, is called your conditional statement. If two lines are perpendicular, then they intersect. The converse of that statement, flip-flop. Okay? You just exchange the if and then. Another example. Oh, we just did this one. I could make an upside down T when I type. Okay. So, yeah, what will happen here, there's actually going to wind up being 4 of these. We're going to have 4 of these. We're going to have what's called the conditional, which is P implies Q. The converse, Q implies P. The inverse, I'm going to show another symbol. An inverse is when you negate a statement. In order to negate a statement, what word do you have to put in there? What does negate mean? If I want to say negate, if I want to put what's called if I want to negate a statement, I would say, if I wanted to say, this is a piece of paper. Okay? To negate that, I would say, this is not a piece of paper. It's just basically putting the word no in it. Okay? Okay? I'm putting no, not one of those in there. So what we say is, there's a symbol for the word no, because the word no is too long. Not P implies not Q. So inverse means not P implies not Q. All right. So conditional, P implies Q. Bless you. Converse, Q. Tosh, stop. People are trying to write stuff down and listen to what I'm saying. Please distracting other people. Please stop distracting other people. Josh, I'm asking you to stop talking because it's distracting other people. Thank you. What part of this did you not understand? I just said it. Stop talking. It's that simple. Conditional, P implies Q. Converse, Q implies P. Inverse, not P, not Q. And then the last one, which is the weirdest sounding one, is called the contrapositive. What the contrapositive does, it's not Q is not P. And this actually flows really cleanly if we use the simple example in a minute here with that our lines being perpendicular. And I'll show you how all this works. Not Q implies not P. Then we go from there. So go back to our original example. The first example we said where we made an if-then statement, we made a conditional statement. If lines are perpendicular, then they intersect. And we all agreed that that was a true statement. So our conditional one was if two lines are perpendicular, then they intersect. And we said that was true. Not a big deal. Okay? So that was our conditional, and it was a true statement. The next one we did was the converse, where we flip-flopped them. And we said, if two lines intersect, then they are perpendicular. And what did we say about that? Was that true or false? That was false. We said that was false, and the counterexample that we gave was you can have two lines that intersect, and this could be 100 degrees. Very, very simple way of doing it. You can say two lines can intersect that don't equal 100. You can write, they could be two lines can intersect to be the same line. There's a bunch of different ways of writing that out. Excuse me. The inverse then goes back to your original. The original was if two lines are perpendicular, then they intersect. This tells me to put the word not on both sides. Inverse. Not P implies not Q. If two lines do not, or excuse me, two lines are not perpendicular, then they do not intersect. Correct. That is false. Okay. If two lines are not perpendicular, then they do not intersect. Notice how we just threw the all we had to do there was throw the word in not on both sides. Okay. Excuse me. So what's another counterexample for that? What's it? You're right, it's false, but what's your counterexample?
You can draw the same thing.
Exactly. In this case, you can draw the exact same diagram by saying that's 100 degrees. And that's a perfectly fine counterexample, because what you're saying here is if two lines are not perpendicular, they don't intersect. Well, those two lines aren't perpendicular, and those two lines still intersect. A lot of times, the idea of the counterexample, more often than not, doesn't have to change. If we go through the whole idea of if you are a teenager than you are 15, you can counterexample that idea pretty much straight through for most of them, with the same thing of being, oh, you can be 17, depending on how you flip-flop things around. Okay. So the inverse, if two lines are not perpendicular, then they do not intersect. And then the counterpositive is just basically taking that statement and flipping it. So we already have all of our nots in the statement itself. So if I write it out, I would just say if two lines do not intersect, then those two lines are not perpendicular. Correct. Two lines do not intersect. Then they are not perpendicular. And just like Josh said a second ago, that is a true statement. Because if you have two lines that don't intersect, will they ever be perpendicular? No. Right? So that's a true statement.
Unless they're like facing each other.
The idea here is that we're going to take statements and we're going to write them out in terms of what's called the conditional, if then, converse, flip-flop, inverse, not if, not then, and then the other one just flip-flop that one. So really, if you can come up with the first statement, your first if-then, the rest of it is just putting a couple extra words to it and rewriting it. Okay? Please put your phone away. Okay. Let's see. Let's do. Write the converse, inverse, and contrapositive of a non-math thing. I have the conditional up here for you. Write out the other three, please. It's all up to interpretation. And that's what a lot of this stuff gets to. There are some pretty interesting interpretations for some of these things. And if you have counterexample for it, you can use counterexample for it. This is why I always say that students in high school, I mean, Lord knows you guys know how to argue. You're actually using arguments valid with validity now. Okay. This is how you can come up with a valid argument. Take a second and write that out. Yeah, diagrams are totally fine for disproving something, and it's fine. Okay. Conditional. If it is raining, then it is cloudy. Okay. Well, I think Josh, that's kind of where you're getting it. Well, sometimes it's raining in one spot, but the sun's out over here, so it could be partly sunny. No. So, how about we say this is true-ish? But we could say that for intensive purposes, let's say we could say that it could be partly sunny. The clouds are what hold the moisture in after a certain. There's moisture in the air, is what, and then it says the accumulation of moisture which creates the cloud. I see. There's a lot of stuff there. Converse, flip-flop it. If it's cloudy, then it's raining. True or false? False, because it could just be plain old boring cloudy. Kind of. You see what I'm saying? About just throwing in a real generic statement about it? It's kind of what you do. Okay. Inverse. Not raining, then it's not cloudy. True or false? False, because it could just be cloudy out. What's that? Right. It's the idea. It's if it's not raining, then it is not cloudy. That just means it could just plain old be boring cloudy. Yes, ma'am. No, because you have to have the words "not" in here. Remember, it's not P, not Q. All right. I can use the exact same thing here. And then the last one, because I'm running out of time, I want to make sure I give you guys the homework here. If it's not cloudy, then it's not raining. And that's kind of like one of those true-ish statements, because technically, it could be cloudy on one side, it could be the sun could be coming out on the other, it could be on the other side of the rainstorm. Yeah. Now, what we have tonight, it might take us a couple days to get through, which is not the end of the world. All right. A lot of these are give a counterexample. Is this a true or false statement? Things like that. All right. This is all in the book, so you have to use the Pearson tabs to get through it. I'll have it posted up on the calendar here in a minute, but for the most part, it is extraordinarily straightforward. Okay, and Christian, I know you're looking at it right now, and the instructions on it are pretty easy. Okay, We'll continue working through some of these again tomorrow, because it usually takes a good day or so to get started through 2-2 with a lot of the writing. Yes, ma'am? I don't know, whenever we get through all of it. Yeah, I want you to get through as much of that as you can. Guys, ladies and gentlemen, it's not that much stuff, guys. We're talking 12, 13 problems. Some of those things are quick, like give a counterexample. All right? Yeah, it just looks bad. Okay? I expect this to be done tomorrow. Obviously, you might have a question here or there, but it's not that much.